A black hole begins to form when a massive star runs out of fuel to keep burning. Without that fuel, the outward pressure from nuclear reactions stops. Gravity then takes over and pulls everything inward. The star's core collapses, and if it is heavy enough, the collapse continues past the point where even light cannot escape. At this stage, a black hole forms. For example, think of a star much larger than our Sun. During its life, the star burns hydrogen into helium, and later heavier elements like carbon and iron. When it can no longer produce energy, the balance between pressure and gravity breaks. The outer layers explode in a supernova, while the core shrinks. If the core's mass is at least 3 times the mass of the Sun, gravity crushes it into a point called a singularity, surrounded by an event horizon. The event horizon is like a one-way door. Anything that crosses it, even light, cannot escape. Imagine dropping a ball into a deep well. If the well is endlessly deep and the walls are smooth, the ball can never climb out. In space, this well is made of curved space-time caused by intense gravity. Black holes vary in size. Some are only a few times more massive than the Sun. Others, found in the centers of galaxies, have millions or billions of solar masses. These supermassive black holes likely formed from smaller ones merging over time, or from the collapse of massive gas clouds in the early universe. Scientists study black holes by observing their effects on nearby stars and gas. When matter falls toward a black hole, it heats up and glows, releasing X-rays. Telescopes detect this radiation, giving clues about the black hole's size and behavior. In 2019, astronomers even captured an image of a black hole's shadow using a network of telescopes around the world. While black holes are powerful, they do not act like cosmic vacuum cleaners. Objects must pass very close to be pulled in. If our Sun were replaced by a black hole of the same mass, Earth would keep orbiting as before, though without sunlight, black holes shape galaxies and play a role in how stars form and die, making them key to understanding the universe. A black hole's gravity is so strong that nothing, not even light, can get away once it gets too close. This happens because the mass of the black hole is packed into a very small space. The closer you get, the stronger the pull becomes at a certain boundary, called the event horizon. Escape is impossible. Light normally travels in straight lines, but near this boundary, space itself curves so much that light bends inward and never comes back out. Imagine trying to throw a ball into the air. On Earth, if you throw it fast enough, it escapes into space. This speed is called escape velocity. A black hole's escape velocity is higher than the speed of light, which nothing can reach. That is why even light cannot break free. To an outside observer, this makes the black hole look completely dark. When matter falls toward a black hole, it does not vanish right away. It first swirls around in a disk called an accretion disk. As the gas and dust spin closer to the event horizon, they heat up and glow, releasing powerful X-rays. Scientists use special telescopes to detect this radiation. This is one way they can study black holes, even though they cannot see the black hole itself. The intense gravity also affects nearby stars. For instance, if a star orbits an invisible, massive object and moves in a strange way, astronomers can figure out that a black hole is there. This is how they confirmed a supermassive black hole sits at the center of our galaxy, the Milky Way. Think of it like a whirlpool in water. As you get closer to the center, the current becomes stronger and faster. If you cross a certain point, you cannot swim back out. A black hole works the same way, but with gravity instead of water. This extreme pull makes black holes some of the most fascinating and mysterious objects in space. The event horizon is the boundary around a black hole where escape becomes impossible. Once something crosses this point, it cannot return, not even light. This happens because the gravity inside the event horizon is so strong that all paths lead inward. From the outside, it looks like a dark sphere, but there is no physical surface there, just a limit in space where the rules change. Imagine standing near the edge of a waterfall. Upstream, you can still paddle against the current and move away. But once you pass the edge, the current is too strong, and you are carried over no matter how hard you try. The event horizon works the same way, but instead of water, it is the fabric of space and time that flows inward toward the black hole. Objects approaching the event horizon experience extreme effects. To a distant observer, they appear to slow down as they get closer, never seeming to cross the boundary. Their light stretches to longer, redder wavelengths, eventually fading until it disappears. To the falling object itself, though, it crosses the event horizon without noticing a sharp change, moving deeper into the black hole's gravity well. The size of the event horizon depends on the black hole's mass. For a black hole, with the mass of our Sunday, the event horizon would be only about 3 kilometers across. For a supermassive black hole, like the one at the center of the Milky Way, the event horizon spans millions of kilometers. Astronomers cannot see the event horizon directly, but they can detect its effects. In 2019, the Event Horizon Telescope captured the shadow of a black hole by linking radio telescopes around the world. This image showed the dark center surrounded by a bright ring of glowing gas, giving the first direct visual evidence of an event horizon's boundary. The event horizon marks the point of no return and defines what makes a black hole so extreme. Outside it, matter and energy can still interact with the universe. Inside, everything is trapped, adding to the black hole's mass and changing how it shapes its surroundings. This invisible boundary is key to understanding how black holes work and why they remain such a profound mystery in astrophysics. Black holes come in 3 main sizes: stellar, intermediate, and supermassive. Stellar black holes form when massive stars run out of fuel and collapse. After the star's outer layers explode in a supernova, the remaining core is crushed by gravity. These black holes are usually between 3 and a few dozen times the mass of the Sunday. Imagine a star 10 times heavier than the Sunday dying. Its core collapses into a space only a few kilometers wide, yet it keeps the same mass. If our Sunday were replaced by a black hole of equal mass, Earth would still orbit as before, but without light or heat. Intermediate black holes are harder to study because they are rare and harder to detect. Their masses range from a few hundred to a few thousand suns. Scientists think they form when several stellar black holes merge or when very dense star clusters collapse. One possible example is a black hole found inside a star cluster in a nearby galaxy. Detecting them is like trying to find a single dark object in a crowded, distant neighborhood. Astronomers look for signs such as stars moving strangely or gas glowing as it falls toward the black hole. Supermassive black holes are the giants. They have millions or even billions of times the Sunday's mass. These are found at the centers of galaxies, including our own Milky Way. The one in our galaxy, called Sagittarius A, has a mass equal to 4 million suns. To picture its size, imagine a sphere larger than the orbit of Mercury packed with unimaginable weight. These black holes likely grew over billions of years as smaller ones merged and gas accumulated. Some formed from massive clouds of gas collapsing directly in the early universe. Supermassive black holes can shape entire galaxies. When material falls into them, it heats up and releases huge amounts of energy. This can create bright jets and powerful radiation seen across space. Quasars, for instance, are young galaxies with very active supermassive black holes at their cores. By studying these, scientists learn how galaxies and black holes grow together. Each type of black hole gives clues about how stars evolve, how matter behaves under extreme conditions, and how the universe has changed over time. The smallest known black holes are only a few miles wide, yet they contain more mass than our Sunday. These are stellar black holes formed when massive stars run out of fuel and collapse under their own gravity. During this collapse, the star's core gets crushed into an incredibly dense point called a singularity. The space around it warps so much that not even light can escape once it crosses the event horizon. Even though these black holes are small in size, their gravity is intense. To picture this, imagine taking the mass of the Sunday and squeezing it into a sphere the size of a city. A stellar black hole like this might be only 3 to 10 miles across. Despite its small size, its pull would be so strong that any nearby matter would fall toward it, creating a swirling accretion disk of superheated gas and dust. This disk glows in X-rays, which astronomers can detect with specialized telescopes. It's one of the few ways to find a black hole, since the black hole itself is invisible. An example is a black hole discovered in our Milky Way that weighs about 5 times the mass of the Sunday, but is only about 20 miles wide. It formed when a star much larger than the Sunday exploded in a supernova. The outer layers blasted into space while the core collapsed. If the core had been lighter, it might have become a neutron star instead, because it was heavy enough. Gravity kept pulling inward until a black hole formed. These tiny black holes are common across galaxies, but they are hard to detect unless they interact with other stars or gas. If a black hole is part of a binary system, where 2 stars orbit each other, it can pull material from its companion star. This process creates bright X-ray emissions, making the system easier to study. Even though a stellar black hole is small, it does not act like a cosmic vacuum cleaner. Objects must pass very close to be pulled in. If our Sunday was suddenly replaced by a black hole of the same mass, Earth would keep orbiting at the same distance. The difference is that the solar system would be cold and dark, with no sunlight to support life. The largest supermassive black holes hold billions of times the mass of our Sunday. These giants sit at the centers of galaxies, shaping how those galaxies grow and evolve. Even though they are incredibly heavy, they are spread over a much larger area than smaller black holes. For example, the supermassive black hole at the center of the Milky Way, Sagittarius A, has about 4 million solar masses. In comparison, some of the biggest known black holes found in distant galaxies reach more than 10 billion solar masses. To picture this, imagine packing the mass of billions of suns into a single region of space. The event horizon of such a black hole could stretch wider than our entire solar system. One of the largest ever found, called Ton 618, has a diameter of hundreds of billions of miles. Its gravity is so intense that it controls the motion of stars, gas, and even dark matter across its galaxy. These enormous black holes likely formed in the early universe. Scientists believe they started as smaller black holes created by collapsing stars or massive clouds of gas. Over billions of years, they grew by swallowing gas, dust, and entire stars. Sometimes 2 galaxies collide, and their central black holes merge, creating an even larger one. This slow build-up explains how supermassive black holes became so huge today. When matter falls toward one of these giants, it heats up and produces massive amounts of energy. This can create jets that blast particles far into space and light up the galaxy's core. Quasars are a striking example of this process. They are young galaxies with extremely active supermassive black holes at their centers, so bright they can outshine the rest of their galaxy. Astronomers study these giants by watching how nearby stars move. If a cluster of stars orbits an invisible object at extreme speeds, it points to the presence of a supermassive black hole. This method confirmed Sagittarius A in our Milky Way. In 2019, the Event Horizon Telescope captured the first image of a black hole shadow, showing the glowing ring of material around one in another galaxy. These discoveries help scientists understand how such colossal objects form and how they influence the universe around them. At the heart of our galaxy lies a supermassive black hole called Sagittarius A, often pronounced Sagittarius A star. It sits about 26,000 light years from Earth in the direction of the Sagittarius constellation. This black hole has a mass equal to about 4 million suns, yet it fits inside a space smaller than the orbit of Mercury. Despite its size, it does not swallow everything around it. Most stars in the Milky Way are far enough away that they continue to orbit safely, just as planets orbit the Sun. Astronomers discovered Sagittarius A by tracking the movement of stars near the center of the galaxy. These stars were moving at incredible speeds, as if they were being pulled by a massive invisible object. One star, known as S2, completes a full orbit around Sagittarius A in just 16 years. This close, fast movement provided strong evidence that a supermassive black hole was there. Sagittarius A is quiet compared to black holes in some other galaxies. It does not consume large amounts of gas or stars very often, so it does not shine as brightly. When it does pull material inward, the matter heats up and gives off bursts of X-rays and radio waves. Telescopes on Earth detect these signals, helping scientists study its behavior. In 2022, the Event Horizon Telescope captured an image of Sagittarius A. This image showed a glowing ring of hot gas around a dark center, the shadow of the black hole itself. It was a major achievement, proving what had been suspected for decades. If the Sun were suddenly replaced by a black hole with the same mass, Earth's orbit would stay the same. The main difference would be that sunlight would vanish, leaving the planet cold and dark. The same idea applies to Sagittarius A. Its gravity keeps nearby stars in motion, but it does not pull in everything in the galaxy. Only objects that come very close are in danger of falling past its event horizon. Sagittarius A helps scientists understand how galaxies form and evolve. By studying it, researchers learn about black holes in general and about the forces that shape the Milky Way itself. Black holes are often pictured as giant cosmic vacuums that suck everything around them. But this is not how they work. They pull objects in with gravity, just like stars, planets, and other massive bodies do. The difference is that black holes have an incredibly strong gravitational field because their mass is packed into a very small space. If our Sun were suddenly replaced by a black hole of the same mass, Earth would keep orbiting in the same path. The pull of gravity would stay the same. The only change would be the loss of sunlight and heat, leaving the solar system cold and dark. This shows that black holes do not reach out and drag things in from far away. An object must come close to a black hole for its gravity to dominate. Imagine a whirlpool in a river. From a distance, the water flows normally, and you can paddle safely. As you get closer to the whirlpool, the current strengthens. If you cross a certain point, you cannot escape and are pulled inward. A black hole acts like this, except it bends space itself rather than water. The boundary where escape becomes impossible is called the event horizon. Once something crosses it, it cannot return. Matter that falls toward a black hole does not disappear right away. It often swirls around first, forming a glowing disk of hot gas and dust called an accretion disk. This disk gives off X-rays and other radiation as the material heats up. Astronomers use telescopes to detect these signals and locate black holes, even though the black holes themselves are invisible. Sometimes, black holes interact with nearby stars. In a binary system, a black hole can pull gas off its companion star. This process creates bright emissions and powerful jets of particles that shoot into space. These signs help scientists study how black holes behave. Black holes are intense, but they follow the same rules of gravity as everything else in the universe. Their reputation as cosmic vacuums comes from misunderstanding how they work. Unless an object travels too close, it will continue to orbit or drift without being pulled inside, just as it would around any other massive object. Time behaves differently near a black hole because of an effect called gravitational time dilation. Gravity warps space and time, and the stronger the gravity, the more extreme the effect. Near a black hole, where gravity is incredibly intense, time moves much more slowly compared to places farther away. Imagine two people, one stays far from the black hole, while the other moves close to its event horizon. To the person near the black hole, their clock ticks normally. But to the observer far away, that same clock appears to run slower and slower as it approaches the event horizon. At the edge, time seems to almost stop from the distant perspective. Our simple way to picture this is by thinking about standing on a tall mountain versus standing at sea level. Gravity is slightly stronger at sea level, so time runs a tiny bit slower there. This difference is so small, it takes extremely precise instruments to detect. Near a black hole, the difference is enormous. This effect was shown in the movie Interstellar. In one scene, astronauts visit a planet close to a black hole. They experience only a few hours on the surface, but when they return to their ship, many years have passed for someone who stayed farther away. While this was a fictional example, the science behind it is real. Gravitational time dilation also explains why objects falling into a black hole appear to freeze in place from far away. As the object approaches the event horizon, the light it emits stretches to longer, redder wavelengths and fades until it disappears. To the distant observer, it looks like the object never fully crosses the boundary, even though, from its own point of view, it passes through without noticing a sharp change. Scientists use this principle to study black holes and test general relativity. Telescopes can track how light behaves near extreme gravity, providing evidence for time dilation. This same effect is important in everyday life too. GPS satellites orbiting Earth experience a weaker gravitational field than we do on the surface, so their clocks run slightly faster. Engineers must adjust for this difference to keep navigation accurate. Near a black hole, these corrections would be far greater, showing how powerful gravity's effect on time can be. If you fell into a black hole, the pull of gravity would increase so quickly that different parts of your body would feel very different forces. This process is called spaghettification because it stretches objects into long, thin shapes, like a noodle. The effect happens because gravity gets stronger the closer you are to the black hole. Your feet, being nearer to the center, would feel a much stronger pull than your head. At the same time, the sides of your body would be squeezed inward. Imagine standing on Earth, where gravity pulls on you evenly. Now picture standing near a black hole. The difference between the gravity at your feet and your head would be extreme. At some point, the difference becomes so great that it tears apart anything, even atoms. This happens well before you reach the singularity, which is the point at the very center where matter is crushed into infinite density. For small black holes, spaghettification would happen quickly, long before you cross the event horizon. You would be stretched and broken apart almost instantly. With a supermassive black hole, like the one at the center of the Milky Way, the event horizon is so large that you might cross it without noticing at first. The stretching would begin only once you got much closer to the center. From an outside observer's point of view, you would appear to slow down as you approached the event horizon. Your image would fade and shift to redder colors until it disappeared completely. To you, however, time would seem normal. You would keep falling inward, unaware of how strange you appeared to the person watching from far away. When a star gets too close to a black hole, its material is pulled apart and forms a glowing stream. Parts of this stream fall inward, while other parts are flung away at high speeds. Telescopes detect this light and help scientists understand what happens in these extreme environments. Spaghettification shows just how powerful a black hole's gravity is. It demonstrates that near these objects the familiar rules of space, time, and matter break down in ways that are hard to imagine but supported by physics. Stephen Hawking made a groundbreaking discovery about black holes in the 1970s. He showed that black holes are not completely black, but can slowly give off tiny amounts of energy. This energy is now known as Hawking radiation. It comes from quantum effects near the event horizon, where space is never completely empty. Even in a vacuum, pairs of particles and antiparticles constantly pop in and out of existence for brief moments. Near a black hole's edge, one particle in the pair can fall into the black hole while the other escapes. When this happens, it looks as though the black hole has emitted a particle. Over time, this process causes the black hole to lose a very small amount of its mass. The effect is incredibly slow for large black holes. For example, the supermassive black hole at the center of the Milky Way would take many times the current age of the universe to shrink even slightly. As they lose mass, they would give off more radiation and eventually evaporate completely in a burst of energy. These small black holes are only theoretical, but if they exist, they could release powerful signals as they vanish. Hawking's idea was surprising because, before this, scientists thought nothing could escape from a black hole. Once it crossed the event horizon, his theory linked gravity, quantum mechanics, and thermodynamics, three key areas of physics. It also showed that black holes have a temperature and entropy, like ordinary objects. No one has directly detected Hawking radiation yet, because it is extremely faint. Still, researchers study similar effects in labs using special materials and devices to mimic the conditions near a black hole. These experiments help test whether Hawking's theory matches what we see in nature. This discovery changed how scientists think about black holes. Instead of being eternal traps, black holes slowly fade over unimaginable lengths of time. Even the most massive ones will eventually vanish, leaving only the radiation they gave off. Hawking's work opened new questions about what happens to information that falls into a black hole and how the universe behaves at its most extreme limits. Hawking radiation shows that black holes are not permanent. Over immense stretches of time, they can slowly lose mass and energy, a process often described as evaporation. This happens because pairs of tiny particles constantly form near the event horizon. Normally, they appear and vanish together, but near a black hole, one particle can fall in while the other escapes. The escaping particle carries away a small amount of the black hole's energy, making it shrink just a little. For most black holes, this process is incredibly slow. A supermassive black hole, like the one at the center of the Milky Way, would take far longer than the current age of the universe to evaporate. Its mass is so large that the energy loss from Hawking radiation is almost unnoticeable. Even a stellar black hole, which is much smaller, would last for trillions of years before fading completely. Teeny black holes, if they exist, would evaporate much faster. As they lose mass, they would release more and more radiation in a runaway effect. In their final moments, they could give off a powerful burst of energy, like a small explosion. Scientists have not found one of these yet, but they continue to search for signals that might reveal their presence. The idea of black hole evaporation was revolutionary because it challenged the belief that nothing could escape a black hole. It also connected three important fields of physics: gravity, thermodynamics, and quantum mechanics. It suggested that black holes have temperature and entropy, just like ordinary matter. While no one has directly detected Hawking radiation, researchers study its effects using advanced experiments. Some lab setups create conditions that mimic how particles behave near a black hole's edge. These help test whether Hawking's theory matches what happens in nature. If black holes truly evaporate, it means even the darkest, most massive objects in the universe are temporary. Given enough time, they will slowly fade away until nothing remains but the radiation they gave off. This discovery reshaped our understanding of black holes, showing that they are not eternal prisons for matter and energy, but part of a cycle that continues long after the stars around them have burned out. Some black holes rotate so fast that the edge of their event horizon moves at nearly the speed of light. This spin comes from the stars or gas clouds that formed them. When a massive star collapses, any rotation it had is conserved, just like a spinning ice skater who pulls in their arms to spin faster. As the core shrinks into a black hole, its spin rate increases dramatically. A spinning black hole behaves differently from one that does not rotate. It drags the space around it in a process called frame dragging. This effect twists space and time near the black hole, forcing nearby matter, and even light to move in the direction of the spin. The region where this twisting happens is called the ergosphere. In this zone, nothing can stay still, but unlike inside the event horizon, escape is still possible. The faster a black hole spins, the more energy it can release. For example, when gas and dust spiral toward the black hole, the spin can fling some material outward in the form of powerful jets. These jets shoot particles across thousands of light years and are visible to telescopes on Earth. Quasars, which are some of the brightest objects in the universe, often form around rapidly spinning supermassive black holes. Scientists measure a black hole's spin by studying the light and X-rays given off by the matter in its accretion disk. The inner edge of the disk moves differently depending on how fast the black hole rotates. For instance, a black hole with little or no spin allows the disk to stop farther out, while a fast spinning one pulls the inner disk closer, creating more intense radiation. One black hole in a distant galaxy has been measured spinning so close to the speed of light that its outer edge moves at more than 90% of light speed. This incredible speed shows how extreme these objects can be. The spin also plays a role in how black holes grow. When two black holes merge, their spins combine, creating a new black hole with a different rotation over time. This spin affects how the black hole interacts with its galaxy, influencing star formation and the movement of nearby matter. Even though we cannot see a black hole directly, its spin leaves clear fingerprints on the space around it. A spinning black hole does more than just pull objects inward with gravity. It also twists the very fabric of space, time around it, a phenomenon called frame dragging. This happens because the black hole's enormous mass and rapid rotation create a swirling effect. Anything nearby, even light, is forced to move in the direction of the spin. Imagine stirring thick honey with a spoon. The honey near the spoon starts to swirl, and the motion spreads outward. A spinning black hole works the same way, but instead of honey, it stirs space and time itself. The closer something gets to the black hole, the stronger this twisting becomes. The region where frame dragging is strongest is called the ergosphere. It sits just outside the event horizon. In the ergosphere, no object can remain still, because space-time is being pulled along so powerfully. However, unlike inside the event horizon, escape is still possible if an object moves fast enough in the right direction. This makes the ergosphere unique. It is a zone where strange and energetic events can happen. Scientists think frame dragging helps explain how some black holes produce enormous jets of particles that shoot out into space at nearly the speed of light. The spin transfers energy to the matter swirling in the accretion disk, which then channels that energy into powerful beams. These jets can stretch for thousands of light years and are visible to telescopes on Earth. Frame dragging is not limited to black holes. It also occurs near other spinning massive objects, like Earth, though the effect here is very weak. In 2004, NASA's Gravity Probe B mission measured tiny twists in space, time caused by Earth's rotation. Near a black hole, however, the effect is millions of times stronger. Astronomers study frame dragging by looking at the light and X-rays emitted by gas near a spinning black hole. These signals show how matter moves and how space-time is being warped. This information helps scientists measure how fast a black hole spins and how it shapes its surroundings. Frame dragging shows that black holes don't just pull on matter, they reshape the universe itself in a way that challenges our everyday sense of motion and time. When two black holes get close enough, their gravity pulls them into a slow spiral. Over time, they move faster and closer together until they finally collide and merge into a single larger black hole. This process releases an enormous amount of energy, but not as light or heat. Instead, it ripples through space, time as gravitational waves. These waves stretch and squeeze space itself, like ripples spreading across a pond after a stone hits the water. Gravitational waves travel at the speed of light and carry information about the black holes that created them. The final moments of the merger produce the strongest signal. In those last seconds, the two black holes orbit each other at nearly half the speed of light before slamming together. The energy released in this instant can be greater than the light from every star in the observable universe combined, though we cannot see it with our eyes. Scientists first detected these waves in 2015 using the LIGO observatories in the United States. LIGO uses powerful lasers and mirrors to measure incredibly tiny changes in distance caused by passing gravitational waves. The signal matched the predicted pattern of two black holes merging more than 1 billion light-years away. This discovery confirmed a key prediction of Einstein's theory of general relativity and opened a new way to study the universe. Since then, researchers have detected many more black hole mergers. Each event provides clues about how black holes form and where they are found. For example, when stellar black holes collide, the final black hole is much heavier, showing how these objects can grow over time. In some cases, 3 or more black holes may even merge in stages, creating increasingly massive ones. Gravitational waves also help reveal things we cannot see with regular telescopes. They pass through space without being blocked by dust or gas, carrying clear information about violent cosmic events. By studying these signals, astronomers can map black hole populations across the universe and test theories about how galaxies evolve. The merging of black holes is one of the most extreme events in nature. It shows how matter, energy, and space itself interact under the most intense conditions, giving us a glimpse into parts of the universe that were once completely hidden. In 2015, scientists detected gravitational waves for the very first time, confirming a prediction made by Albert Einstein a century earlier. The signal came from two black holes spiraling together and merging into one. These black holes were located about 1.3 billion light-years away. Each was roughly 30 times the mass of the Sunday, and as they circled each other, they moved faster and faster until they collided. The final moments of the merger were incredibly violent. In just a fraction of a second, the black holes released more energy through gravitational waves than all the stars in the observable universe emit as light. At the same time, this energy rippled outward, stretching and squeezing space itself. By the time the waves reached Earth, they were extremely faint, changing distances by less than a fraction of the width of a proton. The Laser Interferometer Gravitational Wave Observatory, or LIGO, detected this tiny disturbance. LIGO uses 2 giant L-shaped detectors in the United States, one in Washington and one in Louisiana. Each arm of the L is 4 kilometers long. Powerful lasers measure minuscule changes in the length of these arms caused by passing gravitational waves. When the 2015 signal arrived, both detectors recorded the same pattern within milliseconds, confirming it was real. The event was named GW150914, with the numbers representing the date, the 14th of September 2015. This detection was a milestone in science. It provided direct evidence that gravitational waves exist and proved that black holes can merge. Before this, black holes had only been studied indirectly through their effects on nearby stars and gas. The discovery opened a new way of observing the universe. Unlike light, gravitational waves are not blocked by dust or other matter, so they carry clear information about events that would otherwise remain hidden. Since 2015, LIGO and other observatories have detected dozens of similar signals, including some from black holes merging with neutron stars. This first detection also helps scientists test Einstein's theory of general relativity under extreme conditions. The waves matched his predictions perfectly, showing that his theory still holds even in the most violent environments. It marked the beginning of gravitational wave astronomy, giving us a powerful new tool to explore the cosmos. Black holes themselves are completely invisible because no light or any other form of radiation can escape once it crosses the event horizon. This makes them impossible to see directly, no matter how powerful a telescope is. The only way to find a black hole is by observing how it interacts with nearby matter, or by detecting its effects on space and time. One common clue comes from stars. If a star orbits an unseen companion and moves in an unusual way, it can reveal the presence of a black hole. Astronomers track the star's motion to estimate the mass of the hidden object. If the mass is too high to be a regular star or neutron star, it is likely a black hole. This method was how scientists confirmed the existence of the supermassive black hole at the center of the Milky Way. Sagittarius of Fey black holes can also reveal themselves through glowing gas and dust. When matter falls toward a black hole, it does not vanish right away. Instead, it spirals inward, forming an accretion disk. Friction in the disk heats the material to extreme temperatures, causing it to shine brightly, often in X-rays. Telescopes designed to detect these high-energy signals can spot the area around the black hole, even though the black hole itself remains dark. Sometimes black holes produce narrow jets of particles that shoot out at nearly the speed of light. These jets can extend thousands of light years and are visible with radio and optical telescopes. The energy that powers these jets comes from the matter swirling in the accretion disk, and in some cases, from the spin of the black hole itself. If a black hole is not actively feeding on surrounding material, it becomes very difficult to detect. A lone black hole drifting through space would be invisible unless it passed in front of a background star. Even then, it would only be noticed through a subtle effect called gravitational lensing, where its gravity bends the light from the star, briefly making it appear brighter. Because of this, many black holes in our galaxy likely remain hidden. Astronomers estimate there could be millions of stellar black holes in the Milky Way, but only a fraction have been found. These invisible giants quietly shape their surroundings, influencing the motion of stars and gas without ever revealing their dark centers directly. Astronomers cannot see black holes directly, so they study how nearby stars and gas behave to find them. A common method is tracking the movement of stars. If a star appears to orbit an invisible object, its path can reveal what is hidden by measuring the speed and shape of the orbit. Scientists can estimate the unseen object's mass. If it is far too massive to be a regular star or even a neutron star, it is likely a black hole. This is how astronomers confirmed the presence of Sagittarius, a Fey, the supermassive black hole at the center of the Milky Way. One star, known as S2, moves so fast around this point that only a black hole with millions of solar masses could explain its motion. Gas clouds also reveal clues. When gas falls toward a black hole, it forms a swirling disk called an accretion disk. Friction in this disk makes the gas extremely hot, causing it to shine in X-rays and other high-energy radiation. Telescopes that can detect this radiation, like NASA's Chandra X-ray Observatory, allow scientists to study what happens near a black hole's edge. The brighter and hotter the disk, the more actively the black hole is feeding on surrounding matter. Sometimes, matter falling into a black hole produces powerful jets of particles that shoot out at nearly the speed of light. These jets stretch across thousands of light years and can be seen with radio and optical telescopes. They help astronomers pinpoint the black hole's location and understand how it affects its galaxy. Another method involves gravitational lensing. When a black hole passes in front of a distant star, its gravity bends and focuses the star's light, making the star appear brighter for a short time. This effect is rare, but offers a way to detect black holes that are not actively pulling in gas or stars. Each of these methods gives a different view of how black holes interact with their surroundings. By combining these observations, astronomers can measure a black hole's mass, spin, and growth over time. Even though the black hole itself remains invisible, its presence is clear in the behavior of the stars and gas, caught in its powerful gravitational field. The closest known black hole to Earth is about 1,600 light years away, which is relatively close in cosmic terms. It was discovered in a star system within our own Milky Way. Astronomers identified it by studying the motion of a nearby star that seemed to orbit an invisible companion. By measuring the star's speed and path, they determined that the hidden object had a mass too great to be anything other than a black hole. This black hole is a stellar black hole, formed when a massive star collapsed at the end of its life. Despite being so close compared to other black holes, it poses no threat to Earth. At 1,600 light years away, it is far beyond the reach of its gravitational pull. To put that distance into perspective, light travelling at 186,000 miles per second would still take 1,600 years to reach us. Unlike some black holes that feed on nearby gas and shine brightly in X-rays, this one is quiet. It does not have an active accretion disk or produce strong radiation, making it very difficult to detect. Astronomers had to rely on careful observations over time to spot its presence. The star in the system orbits as if tethered to something invisible, much like a planet circles a star, revealing the black hole's hidden mass. Finding nearby black holes like this helps scientists understand how many of them might exist in our galaxy. Most stellar black holes remain hidden because they are not interacting with surrounding matter. Astronomers estimate there could be millions of them scattered across the Milky Way, moving silently through space. Occasionally, a quiet black hole can be detected through gravitational lensing. This happens when its gravity bends the light from a more distant star, briefly magnifying it. While rare, these events give researchers another way to search for black holes that do not emit any light or radiation. The discovery of the black hole 1,600 light years away shows how advances in technology and observation methods are allowing us to find objects once thought impossible to detect. It also highlights that even the closest black holes are far enough away that they have no direct effect on Earth, serving only as fascinating windows into the life and death of massive stars. If the Sunday were suddenly replaced by a black hole of the same mass, Earth's orbit would not change. Gravity depends on mass, not on what form that mass takes. A black hole with the exact same mass as the Sunday would pull on Earth, in the same way the Sunday does now. Our planet would continue to travel around it along the same path, at the same speed, and at the same distance. The difference would be that without the Sunday's light and heat, Earth would become a cold, dark world almost immediately. Temperatures would drop quickly, freezing the surface and oceans over time. Photosynthesis would stop, cutting off the food chain. Within weeks, most life would not survive, and only deep-sea creatures near hydrothermal vents might continue to exist for a while. This scenario shows that black holes are not cosmic vacuum cleaners that suck in everything nearby. Objects have to get very close to a black hole to fall in at the distance of Earth's orbit. Nothing would change except for the lack of light and warmth. Mercury and Venus would continue circling as well, just like they do now, but they too would be frozen and lifeless. The event horizon of a black hole with the Sunday's mass would be incredibly small, only about 3 kilometers across. By comparison, the Sunday's current diameter is about 1.4 million kilometers. This means the black hole would be almost impossible to see directly. Even though it would hold the same mass, it would appear as a dark, tiny point surrounded by empty space. The planet's continued orbits help explain how astronomers detect black holes. In other star systems, when they see a star moving around an invisible object, they can measure the motion and figure out the unseen companion's mass. If the numbers match what a black hole would have, they know one is there. Replacing the Sunday with a black hole would destroy life on Earth because of the lack of energy. But it would not cause our planet to spiral inward or be swallowed whole. This example helps clarify what black holes actually do. They influence their surroundings through gravity, just like any other massive object, only with a much more concentrated and extreme form of mass. Some black holes produce powerful jets of particles that move at speeds close to the speed of light. These are called relativistic jets. They are most often seen around supermassive black holes at the centers of galaxies. The jets can stretch for thousands, even millions of light years, making them some of the largest structures in the universe. The jets do not come from inside the black hole itself. Instead, they form just outside the event horizon. As matter falls toward the black hole, it spirals into an accretion disk. The intense gravity and friction in this disk heat the material to extreme temperatures, causing it to glow and emit radiation, including X-rays. Some of this material, instead of falling in, gets caught in powerful magnetic fields. These fields funnel the particles along narrow paths and launch them outward at nearly light speed. A good way to picture this is to imagine water swirling down a drain. Most of the water flows inward, but some get sprayed upward and outward by pressure and spin. In a black hole system, gravity and magnetic forces act like that spray, sending matter blasting away in focused beams. Relativistic jets are bright and can be seen across great distances. Quasars, for example, are young galaxies with very active supermassive black holes that produce some of the most powerful jets known. These jets shine so brightly that they can outshine the combined light of all the stars in their host galaxy. Scientists study jets to understand how black holes affect their surroundings. The energy carried by the jets can heat nearby gas, regulate star formation, and even shape the structure of entire galaxies. Observations show that galaxies with active jets often have less gas available to form new stars, suggesting the black hole is influencing its host galaxy's evolution. Relativistic jets also help astronomers locate black holes. By observing the light and radio waves they emit, researchers can trace them back to the black hole's location. Even though the black hole itself remains invisible, the jets serve as a bright, visible sign of its presence. These enormous particle beams are evidence that black holes are not just silent, destructive forces. They are also engines that can release vast amounts of energy, affecting their galaxies on scales far beyond the event horizon itself. Relativistic jets from black holes are some of the largest and most powerful structures in the universe. These narrow beams of particles can stretch for thousands, and sometimes even millions of light years. That means a single jet can span distances far greater than the size of the galaxy where it formed. For comparison, the Milky Way is about 100,000 light years across. Yet some jets are 10 times longer. The jets form just outside the black hole, not from inside it. As gas and dust fall toward the black hole, they spiral into an accretion disk. The intense heat and magnetic fields near the black hole create conditions that force some particles to escape instead of falling inward. These particles are funneled along the black hole's spin axis and blasted outward at nearly the speed of light. Because of this speed, they are called relativistic jets. So picture this. Imagine a spinning fire hose. Most of the water flows straight through the hose and out in a narrow stream. In a similar way, the black hole's magnetic fields focus the flow of particles into straight, powerful beams that travel vast distances through space. These jets glow brightly across many types of light, including radio waves, visible light, and X-rays. Telescopes on Earth can detect this radiation, allowing astronomers to trace the jets back to their source. Even though the black hole itself is invisible, the jets act as a clear sign of its activity. Quasars, some of the brightest objects in the universe, get much of their light from these massive jets. The reach of these jets has a direct effect on their host galaxies. As they move outward, they can heat and push surrounding gas, preventing it from cooling and forming new stars. Over millions of years, this process can change the way a galaxy grows. In some cases, jets also carry material completely out of the galaxy and into intergalactic space, spreading energy and matter far beyond their origin. By studying these enormous beams, scientists gain insight into how black holes influence the universe on a grand scale. A jet stretching thousands of light years shows just how much energy a black hole can release, turning something small and dark into a force that shapes entire galaxies. Supermassive black holes are found in the centers of almost every large galaxy we know of, including our own Milky Way. These giants have masses ranging from millions to billions of times that of the Sun. Despite their size, they occupy a relatively small space compared to the galaxy they sit in. The black hole at the center of the Milky Way, Sagittarius A, has about 4 million solar masses, yet the galaxy itself contains hundreds of billions of stars. Astronomers discovered these black holes by studying how stars and gas move near galactic centers. In many cases, stars orbit something invisible at extremely high speeds, which means a massive but hidden object must be present. The only explanation is a supermassive black hole. Observations of Sagittarius A, for example, show stars whipping around it at thousands of kilometers per second. No other known object could produce such motion in such a small region of space. Some supermassive black holes are quiet, like the one in our galaxy, feeding only on small amounts of matter. Others are very active, pulling in gas and dust that form bright hot accretion disks. When this happens, the black hole can outshine the rest of its galaxy, creating what astronomers call an active galactic nucleus. Quasars are the most extreme examples, where young galaxies with fast-growing supermassive black holes shine so brightly that they can be seen across billions of light years. These central black holes play an important role in shaping their galaxies. The energy from accretion disks and jets can heat surrounding gas, preventing new stars from forming. In some galaxies, the jets extend for thousands of light years, pushing material out and altering the galaxy's growth. This feedback means that galaxies and their central black holes evolve together over time. Evidence suggests that nearly all large galaxies host a supermassive black hole. Small galaxies may not always have one, but in the bigger ones, they seem to be a common feature. Scientists think they may have formed in the early universe, either from massive gas clouds collapsing directly or from smaller black holes merging and growing over billions of years. Their presence today shows that they are a natural part of how galaxies form and change. At the center of the Milky Way sits a supermassive black hole called Sagittarius A, with a mass about 4 million times greater than the Sun. Even though it is so massive, it is compact, fitting inside a region smaller than the orbit of Mercury. Its gravity is strong enough to control the motion of thousands of stars near the galactic core, pulling them into fast orbits that revealed its presence in the first place. Astronomers confirmed its mass by carefully tracking the paths of nearby stars. One of the most studied, known as S2, completes an orbit around Sagittarius A in just 16 years. For comparison, Pluto takes 248 years to circle the Sunday. To move this quickly, S2 must be pulled by something very heavy and very small, and only a black hole fits the data. These observations earned researchers the 2020 Nobel Prize in Physics. Despite its huge size, Sagittarius A is relatively quiet. It does not consume large amounts of matter on a regular basis. Occasionally, gas clouds or small objects drift close, producing flares of X-rays and radio waves as the material heats up before crossing the event horizon. Telescopes around the world, including NASA's Chandra X-ray Observatory and the Event Horizon Telescope, watch these bursts to better understand how black holes behave. In 2022, astronomers released the first image of Sagittarius A captured by the Event Horizon Telescope. It showed a glowing ring of hot gas surrounding a dark center, the shadow of the black hole itself. This image matched predictions from Einstein's theory of general relativity and provided direct visual evidence of the object at the heart of our galaxy. If the Sunday were suddenly replaced with a black hole of equal mass, Earth's orbit would remain the same, just as it would around Sagittarius A. What makes our galaxy's black hole so special is not its ability to swallow stars at random, but the way it anchors the Milky Way, shaping the structure and motion of the central region. Its enormous mass influences the entire galaxy, even if we do not feel its pull directly from our position 26,000 light-years away. Black holes bend light because their gravity is so strong that it warps the space around them. This bending is called gravitational lensing. Light usually travels in straight lines, but near a black hole, space itself is curved. As a result, light from stars or galaxies behind the black hole gets bent around it, reaching observers who would not normally see it. This makes the background object appear distorted, magnified, or even duplicated. Known striking effect is the Einstein ring, where light from a distant object forms a complete circle around the black hole. More often, the light creates arcs or multiple images instead of a perfect ring. These shapes depend on the angle between the observer, the black hole, and the background object. Lensing allows astronomers to detect black holes that would otherwise remain invisible. For example, if a black hole passes in front of a distant star, the star appears brighter for a short time because the light is focused toward Earth. This effect, called microlensing, has been used to find black holes that are not part of binary systems and have no glowing gas around them. Supermassive black holes at the centers of galaxies can create dramatic lensing effects. Their gravity bends light from galaxies far behind them, allowing telescopes to see objects that would normally be hidden. In some cases, lensing helps astronomers study galaxies billions of light-years away, giving insight into the early universe. The bending of light also explains why objects falling into a black hole appear distorted. To a distant observer, the light from the object is pulled and stretched, creating a warped image around the event horizon before it fades away. This is part of what made the first image of a black hole's shadow in 2019 so striking. The bright ring around the dark center was created by light bending around the black hole's gravity. Gravitational lensing is not unique to black holes, but they produce the strongest effects because of their extreme mass. By studying these distortions, astronomers learn more about black holes themselves, the matter around them, and even the structure of the universe on the largest scales. When light passes near a black hole, the extreme gravity bends its path, an effect called gravitational lensing. This bending can make objects that sit directly behind the black hole visible to an observer. Instead of blocking the view, the black hole acts like a lens, curving the light around it so it reaches us from different directions. As a result, we may see multiple images of the same object or a distorted ring, like pattern known as an Einstein ring. Imagine watching a distant star with a black hole between you and it. Normally, the black hole would hide the star. But because its gravity bends the star's light, you could still see it, sometimes in more than one place in the sky. The star might appear stretched into arcs or magnified, depending on the exact alignment. This effect is especially useful for astronomers. It allows them to study galaxies and quasars billions of light years away that would otherwise be invisible. In some cases, lensing by a supermassive black hole in the center of a galaxy has revealed faint background galaxies, offering a glimpse of the early universe. On a smaller scale, lensing can help detect isolated black holes in our own galaxy. When such a black hole drifts in front of a background star, the star brightens for a short time as its light bends around the black hole. This method, called microlensing, provides a rare way to find black holes that are not feeding on nearby matter and would otherwise remain completely hidden. The same bending explains why objects falling near a black hole appear distorted. From far away, the light from the falling object bends around the black hole, wrapping into strange shapes before fading. This effect was part of the iconic 2019 image of a black hole's shadow, where the bright ring of light was formed by glowing gas behind and around the black hole, curved into view by gravity. Gravitational lensing shows that black holes do not just swallow light, they also reshape how we see the universe. By bending light from hidden objects, they act as natural telescopes, allowing us to look deeper into space than we could on our own. In 2019, scientists revealed the first ever image of a black hole, captured by the Event Horizon Telescope, or EHT. This black hole sits at the center of the galaxy M87, about 55 million light years from Earth. The image showed a glowing orange ring of hot gas surrounding a dark central shadow, which marks the black hole's event horizon. It was the first time humanity had seen direct visual evidence of a black hole, confirming predictions made by Einstein's theory of general relativity. The EHT is not a single telescope, but a network of radio observatories spread across the globe. By linking them together using a technique called very long baseline interferometry, scientists created a virtual Earth-sized telescope. This gave the resolution needed to see details as fine as spotting an orange on the moon from Earth. Collecting the data required nights of synchronized observations and then years of processing to combine signals from all the telescopes. The image itself was groundbreaking because black holes are by definition invisible. Light cannot escape once it passes the event horizon. What we saw in the picture was not the black hole itself, but the light from superheated gas swirling around it. As the gas orbited at near light speeds, it glowed brightly before vanishing past the event horizon. The dark center revealed the black hole's shadow, a direct imprint of its immense gravity. The black hole in M87 is a supermassive one, with a mass about 6.5 billion times that of the Sunday. Its event horizon would be larger than our entire solar system. The glowing ring around it in the image was consistent with what scientists had modeled for decades, giving strong evidence that general relativity accurately describes how gravity works in extreme conditions. This achievement was the result of collaboration between hundreds of scientists worldwide. The release of the image marked a turning point in astronomy, showing that even objects once thought impossible to see could be observed with the right tools. Since then, the EHT has continued to study black holes, including capturing an image of Sagittarius A, the supermassive black hole at the center of the Milky Way. In 2022, both images confirmed our understanding of these mysterious giants and opened new ways to explore how they shape galaxies and the universe itself. The first black hole ever imaged was the one in the galaxy M87, located about 55 million light years from Earth. This galaxy, also called Messier 87, is a giant elliptical galaxy in the Virgo cluster. At its center lies a supermassive black hole with a mass around 6.5 billion times that of the Sunday. Its event horizon is so large that it would easily encompass our entire solar system. The image, released in 2019 by the Event Horizon Telescope team, showed a glowing, uneven ring of light surrounding a dark core. The dark region was the shadow of the black hole, caused by its gravity bending and trapping light. The bright ring came from gas heated to extreme temperatures as it spiraled around the black hole at nearly the speed of light. The light appeared brighter on one side because of the black hole's spin and the direction of the orbiting gas, which made the emission stronger toward us. Capturing this image was a global effort. The Event Horizon Telescope is a network of radio observatories across several continents, including facilities in Chile, Hawaii, Spain, and the South Pole. Together, they acted like a single Earth-sized telescope. The data collected was so massive that hard drives had to be flown physically to central processing centers. Scientists then spent years piecing the data together to produce the final image. M87's black hole is also known for producing enormous relativistic jets, beams of particles moving close to the speed of light. These jets extend far beyond the galaxy itself, reaching hundreds of thousands of light years into space. Astronomers had studied these jets for decades, but the 2019 image was the first time they could directly see the black hole that powered them. The success of imaging the M87 black hole confirmed long-standing predictions from Einstein's theory of general relativity. It proved that the shadow of a black hole would look exactly as the theory described, even under the most extreme conditions. For many scientists, it was a direct test of gravity on cosmic scales, and the results matched perfectly. This achievement opened a new era of black hole astronomy. It demonstrated that with enough cooperation and technology, humanity could observe the unobservable, revealing details about objects that were once only theoretical. Black holes rank among the most efficient energy engines in the universe. When matter falls toward a black hole, it forms an accretion disk, a swirling ring of gas and dust, heated to extreme temperatures. As the particles spiral inward, friction and gravity convert much of their mass into energy. This process can release up to 40% of the matter's rest mass as radiation. By comparison, nuclear fusion in stars, including our Sunday, converts less than 1% of mass into energy. This efficiency explains why black holes can power some of the brightest objects in the cosmos. Quasars, for example, are young galaxies with rapidly feeding supermassive black holes at their centers. As gas pours into the accretion disk, it shines so intensely that a single quasar can outshine an entire galaxy of stars. Some quasars are visible billions of light years away, serving as beacons from the early universe. The jets that shoot from many black holes also show this conversion of matter into energy. Magnetic fields near the spinning black hole channel particles into narrow beams moving close to the speed of light. These jets can carry energy across hundreds of thousands of light years, reshaping galaxies by heating and stirring surrounding gas. Without this feedback, many galaxies would look very different from what we see today. Astronomers study black holes, not by seeing the black holes themselves, but by measuring the energy released around them. X-ray telescopes detect the hot inner regions of accretion disks. Radio and optical telescopes trace the jets. Even gravitational wave observatories now pick up signals. When black holes merge, releasing more energy in a fraction of a second than all the stars in the visible universe combined. An everyday comparison helps show the scale of this efficiency. If a car engine could convert matter to energy as effectively as a black hole, a single drop of gasoline could power the car for years. This extreme efficiency is why black holes, despite being invisible, can dominate their surroundings and influence galaxies on enormous scales. Their ability to turn matter into energy makes them not only destructive, but also some of the most powerful engines in existence. Some black holes grow by pulling in stars, gas, and dust from their surroundings. As this material falls toward the black hole, it does not plunge straight in. Instead, it spirals inward, forming a flat, rotating structure called an accretion disk. Friction and gravity in the disk heat the gas to millions of degrees, making it shine brightly in X-rays and other forms of radiation. Although the black hole itself is invisible, the glowing disk makes its presence clear. In binary star systems, a stellar black hole can draw material from its companion star. Gas flows off the star and forms an accretion disk around the black hole. Over time, the black hole consumes this matter, growing heavier. Astronomers detect these systems because the accretion disks produce strong, variable X-ray signals. These bright flashes often reveal the mass and spin of the hidden black hole. Supermassive black holes at the centers of galaxies feed in the same way, though on a much larger scale, clouds of interstellar gas drift inward and join the disk, adding to the black hole's growth. When large amounts of matter fall in, the disk can outshine the galaxy itself, creating what astronomers call an active galactic nucleus. Quasars are the most extreme examples, where the central black hole consumes so much matter that its energy output is visible billions of light years away. The process is not always steady. Feeding often happens in bursts. A star that strays too close can be torn apart by tidal forces, with its remains forming a temporary accretion disk before vanishing past the event horizon. These violent events are known as tidal disruption events, and telescopes have recorded their bright flares as the doomed stars are shredded. Accretion disks also help explain why some black holes produce powerful jets. Magnetic fields in the spinning disk funnel particles outward at nearly the speed of light, creating beams that stretch for thousands of light years. These jets release huge amounts of energy and influence how galaxies evolve by heating gas and limiting star formation. By studying accretion disks, astronomers learn how black holes gain mass and how they shape their cosmic neighborhoods. Even though the black hole itself remains hidden, the glowing, turbulent disk around it provides one of the clearest signs of its existence and activity. Accretion disks around black holes can outshine entire galaxies because of how efficiently they turn matter into energy. When gas and dust fall toward a black hole, they spiral into the accretion disk, where friction and gravity heat them to extreme temperatures. This process can make the disk emit radiation across the spectrum, from visible light to X-rays. In many cases, the energy output from the disk is greater than the combined light of billions of stars in the host galaxy. Quasars are prime examples of this phenomenon. These are galaxies with supermassive black holes at their centers that are actively feeding on huge amounts of matter. As the black hole consumes gas and dust, the accretion disk glows so brightly that the quasar becomes visible from billions of light years away. Some quasars are so luminous they can outshine every other star in their galaxy by 1,000 times or more. The brightness of an accretion disk depends on how much matter is falling in. A black hole that is not actively feeding will remain quiet and nearly invisible, but when gas clouds or even entire stars are pulled in, the resulting disk can flare with extraordinary power. For example, when a star wanders too close, it can be torn apart in a tidal disruption event. The remains form a temporary accretion disk that shines brilliantly before the material disappears into the black hole. Astronomers study accretion disks using specialized telescopes that detect high-energy light, like X-rays and gamma rays. These emissions reveal details about the disk's temperature, structure, and speed. In some cases, the inner edge of the disk orbits so close to the event horizon that it moves at nearly the speed of light, releasing incredible amounts of energy in the process. If we compare this to everyday energy use, the difference is staggering. A black hole's accretion disk can convert up to 40% of the falling matter's mass into energy. By contrast, nuclear fusion in the Sun converts less than 1%. This explains why, even though a black hole is invisible, the disk around it can dominate the light output of an entire galaxy. These blazing disks are not just brilliant. They are key to understanding how black holes grow and how they influence the galaxies that surround them. Not all black holes are active, and many spend most of their time in a dormant state. An active black hole reveals itself when it pulls in gas, dust, or even stars, forming an accretion disk that glows brightly. But if there is nothing nearby to feed on, the black hole becomes quiet and invisible. Without material to heat up and shine, there is no radiation to detect, leaving only its gravitational pull as evidence of its existence. Dormant black holes can drift unnoticed through space. In fact, astronomers believe the Milky Way alone may contain millions of them, but only a small fraction have been found. Detecting these hidden objects is extremely difficult. One way is by observing the motion of stars. If a star orbits an unseen companion with a mass too great to be a neutron star, the invisible partner is likely a dormant black hole. Another method is microlensing, where a black hole passes in front of a background star and bends its light, briefly making the star appear brighter. These rare events can expose black holes that would otherwise remain undetected. Even supermassive black holes can lie dormant. Sagittarius of Phae, the black hole at the center of our galaxy, is quiet most of the time. It occasionally produces small bursts of radiation when gas clouds wander close, but compared to the blazing cores of active galaxies, it is faint. Other galaxies, however, have active supermassive black holes that shine so brightly their accretion disks outshine the combined starlight of the entire galaxy. The difference between an active and a dormant black hole is not permanent. A dormant one can become active again if new material falls within its reach. For example, a star pulled too close might be torn apart, creating a temporary accretion disk that lights up before fading away again. The existence of dormant black holes means that space is filled with far more of them than we can currently see. They remain some of the most mysterious objects in astronomy, influencing their surroundings silently, their presence betrayed only by the stars and gas that wander too close to their hidden gravity wells. Scientists think primordial black holes may have formed in the earliest moments of the universe, just after the Big Bang. Unlike stellar black holes, which are created when massive stars collapse, primordial black holes would have been born from extreme conditions in the infant universe. Right after the Big Bang, matter and energy were packed together at incredible densities. Small fluctuations in that density could have created pockets where gravity was strong enough to collapse directly into black holes. These black holes would be very different from the ones we see today. Some might have been tiny, with masses less than a mountain, while others could have been much larger. The smallest primordial black holes would have evaporated quickly through Hawking radiation, disappearing long ago. Larger ones, however, could still exist today, drifting silently through space. Astronomers have searched for signs of primordial black holes as possible explanations for mysterious phenomena. One idea is that they could make up some or all of dark matter, the invisible substance that accounts for most of the mass in the universe. Because primordial black holes do not emit light, they would be difficult to find, but their gravity could reveal them. For example, they might bend the light of background stars through microlensing, or their mergers might produce gravitational waves, detectable by observatories like LIGO and Virgo. So far, no definitive evidence has been found, but the search continues. Some gravitational wave events might hint at unusually small black holes that do not fit the pattern of normal stellar collapse. If confirmed, these could point to a primordial origin. The idea of primordial black holes is important because it connects cosmology with black hole physics. If they exist, they would provide clues about the conditions of the very early universe, when matter first formed. They could also help explain unanswered questions about the structure of galaxies, the distribution of dark matter, and the long-term evolution of the cosmos, even without proof yet. Primordial black holes remain one of the most intriguing possibilities in modern astrophysics. Primordial black holes, if they exist, could be unimaginably small, some as tiny as an atom in size, yet still hold immense mass. This is possible because black holes compress matter into an incredibly dense state. A black hole the size of an atom could weigh as much as a large mountain, with gravity strong enough to trap anything that comes too close. These ancient black holes are thought to have formed just after the Big Bang, when the universe was extremely dense and chaotic. Small fluctuations in matter and energy could have collapsed directly under gravity, producing black holes of many different sizes. Unlike stellar black holes, which form from dying stars, primordial ones could range from microscopic to many times the mass of the Sun. The smallest of these black holes would not last forever. According to Stephen Hawking's theory, black holes emit tiny amounts of energy known as Hawking radiation. Over time, this radiation causes them to lose mass and eventually evaporate. Atom-sized black holes would disappear quickly on cosmic timescales, possibly ending in bursts of high-energy radiation. Larger primordial black holes, however, could still exist today, silently drifting through space. Scientists have considered whether these black holes could account for dark matter, the mysterious substance that makes up most of the universe's mass. If billions of tiny but massive black holes were scattered across galaxies, they might explain some of the effects we attribute to dark matter. So far, though, no clear evidence has confirmed this idea. Astronomers continue searching for signs of primordial black holes. They might reveal themselves by bending the light of background stars through microlensing or by colliding with other black holes, producing gravitational waves. Some gravitational wave detections have hinted at unusual black holes that do not fit the patterns of stellar collapse, raising the possibility they could be primordial. The idea that something as small as an atom could contain the weight of mountains captures the extreme nature of black holes. If primordial black holes are real, they would be fossils from the very beginning of the universe, holding clues about how matter, energy, and gravity behaved in its first moments. Some scientists and theorists have suggested that black holes might act as portals to other universes. Though this idea remains unproven, the theory comes from the way black holes warp space and time. At their centers lies the singularity, a point where gravity is infinitely strong and the known laws of physics break down. General relativity allows for the possibility that such a region could connect to another part of space, time forming what is known as a wormhole. In this scenario, falling into a black hole might not mean being destroyed, but instead traveling through a bridge to a different universe or a distant region of our own. However, most physicists believe that the intense tidal forces near the singularity would stretch and tear apart any matter that entered, a process called spaghettification, making travel through a black hole impossible in practice. The idea of black holes as gateways became popular in science fiction and has inspired countless stories and films. Movies like Interstellar used this concept to imagine traveling vast cosmic distances by passing through a black hole. While creative, these stories rely on speculation rather than confirmed science. There are also scientific challenges to the idea. Wormholes, if they exist, would likely be unstable. They could collapse instantly or require exotic forms of matter with negative energy to keep them open. No evidence for such matter has been found. In addition, observations of black holes so far only show them consuming matter and energy, not releasing them into another space. Still, the concept remains interesting because it touches on the limits of our understanding. Black holes are extreme objects where gravity, quantum mechanics, and relativity all intersect. Since we cannot yet observe what happens beyond the event horizon, the possibility of hidden connections or new universes cannot be ruled out completely. For now, black holes as portals remain a theoretical idea rather than an established fact. They highlight how much is still unknown about the universe and how black holes push the boundaries of both science and imagination. Some theories suggest black holes could be linked to wormholes, hypothetical tunnels that connect two distant regions of space. The idea comes from solutions to Einstein's equations of general relativity. In these models, the singularity at the center of a black hole could act as one end of a bridge, with the other end opening somewhere else in the universe, or even in another universe altogether. This type of structure is often called an Einstein-Rosen bridge. On paper, it offers a shortcut through space, allowing faster than light travel. In practice, though, these bridges face serious problems. The equations predict that they would be unstable, collapsing before anything could pass through. To stay open, they would require exotic matter with negative energy density, something that has never been observed in nature. Physicists also point out that falling into a black hole, as we know them, would not be survivable. The tidal forces near the singularity would stretch and crush matter long before it could pass to another side. For stellar mass black holes, this spaghettification would happen well before crossing the event horizon. Even with a supermassive black hole, where the tidal forces at the horizon are weaker, the singularity deep inside would still be inescapable. Despite these challenges, the link between black holes and wormholes remains an active area of speculation. Quantum gravity theories, which attempt to unify relativity and quantum mechanics, sometimes hint that wormholes could exist in more subtle or hidden ways. Some models even suggest that entangled black holes might be connected by microscopic wormholes, a concept known as ER-FITR. So far, there is no experimental evidence that black holes connect to wormholes. Observations show black holes behaving as one-way traps. They pull in matter and light, but nothing emerges. Still, the mathematical possibility keeps the idea alive, and it continues to inspire both serious research and science fiction. Whether wormholes exist or not, studying black holes pushes the limits of physics. They represent extreme conditions where our best theories are tested, and it is in these frontiers that ideas like wormholes gain traction as potential, though unproven, solutions. The information paradox is one of the biggest puzzles in modern physics. It asks what happens to information that falls into a black hole. In physics, information means the details about the state of matter, such as the properties of particles that make up an object. According to quantum mechanics, information can never be destroyed, but when something crosses a black hole's event horizon, it seems to vanish forever. Stephen Hawking's discovery of Hawking radiation deepened the problem. He showed that black holes can slowly lose mass and eventually evaporate. If a black hole disappears completely and all the matter and energy inside are gone, what happens to the information about what fell in? If it is truly lost, that would break the rules of quantum mechanics. If it somehow survives, we need to understand how one idea is that information might be encoded in the Hawking radiation itself. As the black hole emits radiation, it could carry away faint traces of the information, though not in any obvious way. Another idea is that information stays on the event horizon in a kind of hologram, never truly entering the singularity. This holographic principle suggests that the surface of the black hole may store all the information about what has fallen in, much like data on a hard drive. There are also theories that black holes could connect to other regions of the universe, or even other universes. If so, the information might escape elsewhere, though this raises further questions about how the laws of physics apply. Some physicists believe the resolution may come from a full theory of quantum gravity, which would unite general relativity with quantum mechanics and explain what happens at the singularity. For now, the paradox remains unsolved. Experiments and observations cannot yet probe what happens inside black holes. However, studying the behavior of black holes, Hawking radiation, and quantum entanglement continues to give new insights. The information paradox is important because it challenges our most basic assumptions about the universe, whether the laws of physics are truly consistent, and whether information can ever be lost. Black holes highlight one of the deepest conflicts in physics, the clash between quantum mechanics and general relativity. General relativity, Einstein's theory of gravity, describes black holes as regions of space, time curved so strongly that nothing can escape. It works extremely well on large scales, explaining how stars, planets, and galaxies move, but it treats space and time as smooth and continuous, without accounting for the tiny, probabilistic effects that dominate in the quantum world. Quantum mechanics, on the other hand, governs particles at the smallest scales. It says energy comes in discrete amounts, and that particles can exist in multiple states until measured. According to quantum theory, information about matter can never be destroyed. This is where the conflict begins. General relativity suggests that when matter crosses the event horizon of a black hole, it is lost forever. Hawking's discovery of Hawking radiation deepened the problem, since it showed black holes could evaporate completely, apparently erasing all information that once fell inside. This contradiction is at the heart of the black hole information paradox. Relativity predicts a smooth collapse into a singularity, where the laws of physics as we know them break down. Quantum mechanics insists that information must survive in some form. Both theories are well tested in their own domains, but black holes push them together in ways that reveal their limits. One proposed solution is the holographic principle. It suggests that the information inside a black hole might be stored on its event horizon, encoded like a two-dimensional surface holding three-dimensional data. This would preserve the rules of quantum mechanics while still fitting with relativity's predictions. Another idea involves quantum entanglement, where Hawking radiation could carry subtle traces of information outward. Physicists also explore the idea that space-time itself is made up of quantum building blocks, so that a theory of quantum gravity might reconcile the two frameworks. String theory and loop quantum gravity are examples of attempts to unify them, though no final answer has emerged. Black holes sit at the intersection of these two great theories. They are natural laboratories for testing ideas about how gravity and quantum mechanics fit together. Until this clash is resolved, our picture of the universe will remain incomplete, and black holes will continue to challenge the foundations of physics. A black hole's surface area is directly tied to its entropy, a measure of disorder or the amount of information it can contain. This idea was first developed by physicist Jacob Bekenstein in the early 1970s. He suggested that when something falls into a black hole, the information about it is not simply lost, but is instead stored on the black hole's surface, the event horizon. The more matter and energy the black hole absorbs, the larger its event horizon grows, and so does its entropy. Stephen Hawking later showed that black holes emit a faint glow of energy, now known as Hawking radiation. This meant that black holes could have temperature, and if they had temperature, they must also have entropy. The formula that describes this is called the Bekenstein-Fay-Hawking entropy, and it shows that a black hole's entropy is proportional to the area of its event horizon, not its volume. This was surprising because in most systems, entropy depends on the amount of matter inside, which scales with volume. To imagine this, think of storing information on a computer. Normally, data is saved in the memory hardware inside the device. For a black hole, however, the memory is not inside, but on the surface. The event horizon acts like a giant data storage sheet, with each tiny patch holding bits of information. This strange property inspired the holographic principle, which proposes that the universe itself might work in a similar way, with the information inside a region encoded on its boundary. The connection between entropy and surface area also helps explain why black holes cannot shrink in a simple way. If two black holes merge, the total surface area of the final black hole is always greater than or equal to the sum of the two original areas. This law mirrors the second law of thermodynamics, which says entropy in a closed system never decreases. Although no one can yet read the information stored on a black hole's surface, the link between entropy and area has become a cornerstone in understanding the relationship between gravity, thermodynamics, and quantum mechanics. It shows that black holes are not just destructive traps, but also complex physical systems with deep ties to the fundamental laws of the universe. Black holes can grow when they collide with neutron stars, some of the densest objects in the universe. A neutron star is the leftover core of a massive star that exploded in a supernova. It is only about the size of a city, but has more mass than the Sun. When a neutron star and a black hole orbit each other closely, they lose energy through gravitational waves, slowly spiraling together until they merge. As the black hole draws the neutron star inward, extreme tidal forces can rip the star apart before it crosses the event horizon. The shredded material may form a brief accretion disk, glowing brightly in X-rays and other radiation. In other cases, the neutron star plunges directly into the black hole with little light produced. Either way, the black hole gains the neutron star's mass, becoming larger. These events are rare but incredibly violent. In 2020, the LIGO and Virgo observatories detected gravitational waves from two separate mergers between black holes and neutron stars. These ripples in space time carried information about the object's masses and confirmed that such collisions really happen. One of the detected neutron stars was about 1.5 times the mass of the Sun, while the black hole it merged with was around 9 times the Sun's mass. The result was a single larger black hole. Collisions like these also help explain how black holes grow over time. A stellar black hole formed from a collapsing star might only be a few times the Sun's mass, but by merging with neutron stars or other black holes, it can gradually increase in size, eventually becoming a much more massive object. Astronomers study these events, not only to understand black holes, but also to learn about neutron stars. Depending on how the neutron star is torn apart, the collision can reveal details about the dense matter inside it, which is still not fully understood. These mergers may also create heavy elements like gold and platinum, enriching the universe with the building blocks for planets and life. By combining gravitational wave data with light from telescopes, scientists continue to learn how black holes grow through mergers. Each detection brings us closer to understanding the life cycles of the most extreme objects in the cosmos. The most massive black hole ever discovered is estimated to weigh about 66 billion times the mass of the Sun. It sits at the center of a giant elliptical galaxy called Holmberg 15A, located in the Abell 85 galaxy cluster, nearly 700 million light-years away. This enormous object is classified as an ultramassive black hole, a step beyond even the largest supermassive black holes usually found in galaxies. To grasp its size, consider that the black hole at the heart of the Milky Way, Sagittarius A, has about 4 million solar masses. That means Holmberg 15A's black hole is more than 10,000 times heavier. Its event horizon, the boundary beyond which nothing can escape, would stretch across hundreds of billions of kilometers, dwarfing the scale of our entire solar system many times over. Astronomers measured its mass by observing how stars in the central region of Holmberg 15 move under the pull of gravity. The speeds and paths of these stars could only be explained if an object of staggering mass were present. No cluster of stars or gas could account for such gravity, leaving a black hole as the only explanation. Black holes of this size are thought to grow through repeated mergers with other black holes and by swallowing enormous amounts of gas over billions of years. In dense galaxy clusters like Abell 85, galaxies collide often, and their central black holes eventually merge as well. Over cosmic time, this process builds up ultramassive black holes that dominate their surroundings. An object with 66 billion solar masses does not just sit quietly. Its influence extends across the galaxy, shaping the motion of stars, controlling the flow of gas, and affecting how new stars form. Although we cannot see the black hole itself, the evidence of its immense gravity shows in every corner of its host galaxy's core. The discovery of such a giant challenges astronomers to explain the limits of black hole growth. While theories suggest black holes can reach extreme masses, finding one this large pushes the boundaries of what models predict. It shows that black holes are not just common features of galaxies, but can grow into some of the most dominant structures in the universe. Black holes can spin at extraordinary speeds, so fast that they come close to the theoretical limit set by physics. This limit, called the Kerr bound, describes the maximum rate at which a black hole can rotate without breaking the equations of general relativity. If a black hole were to spin faster than this bound, its event horizon would disappear, creating a naked singularity, something most physicists believe nature does not allow. When a black hole spins, it drags the space-time around it, a phenomenon known as frame dragging. Near the event horizon, this effect is so strong that everything, even light, is forced to move in the direction of the spin. The region where this happens is called the ergosphere, and it opens the door to some of the most extreme physics in the universe, including the possibility of extracting energy from a spinning black hole. Astronomers measure black hole spin by studying the light and X-rays from accretion disks. Gas orbiting close to a fast spinning black hole can circle nearer to the event horizon than it can around a slower one. The closer it gets, the hotter and brighter it becomes, allowing scientists to infer the spin rate. Observations have shown some stellar, mass black holes spinning at more than 90% of the maximum allowed speed. Supermassive black holes can also rotate rapidly. Their spin is shaped by their history. If they grow mostly by feeding on gas that falls in steadily from one direction, they spin up over time. But if they grow through random collisions and mergers, their spin may slow or become chaotic. Measuring the spins of supermassive black holes helps astronomers understand how galaxies and their central giants evolve together. A near maximal spin also has consequences for the energy released. Fast, spinning black holes can launch powerful relativistic jets, blasting particles across thousands of light years. These jets carry away enormous amounts of energy and play a major role in shaping their host galaxies. That black holes can spin so close to their theoretical limit shows how extreme they are as physical objects. They take gravity, motion, and energy to the very edge of what our current theories can describe, making them natural laboratories for testing the laws of physics under the most extreme conditions. At the very center of a black hole lies the singularity, the region where physics as we know it no longer works. According to general relativity, once matter crosses the event horizon, it is crushed inward by gravity until it reaches a point of infinite density and zero volume. In this state, the equations of relativity predict values that cannot exist in the real world, such as infinite curvature of space-time. This is why scientists say the laws of physics break down at the singularity. In a stellar black hole, the singularity is thought to be a point. In a rotating black hole, described by the Kerr solution to Einstein's equations, the singularity may form a ring instead of a point. Both possibilities challenge our understanding because no current theory can fully describe what actually happens inside. The singularity cannot be seen directly. It is hidden behind the event horizon, which traps all light and signals from escaping. To an outside observer, matter falling in appears to freeze near the event horizon due to time dilation. but in reality, it continues inward until it reaches the singularity. Once there, the known laws of space, time, and matter no longer apply. Physicists believe the singularity may not be a true point of infinite density, but rather a sign general relativity is incomplete. To explain it, we need a theory of quantum gravity, which would merge quantum mechanics with relativity. Such a theory might reveal that space and time themselves are made of discrete building blocks, preventing actual infinities from forming. The singularity also fuels speculation about ideas like wormholes or alternate universes, though no evidence supports these possibilities. What is certain is that the singularity marks the limit of our knowledge. It is a boundary where our current models fail, making black holes natural laboratories for testing new physics. For now, the singularity remains hidden and mysterious, a place where matter is crushed beyond recognition, and the universe's most fundamental rules reach their breaking point. It stands as one of the strongest clues that our understanding of gravity and quantum mechanics is not yet complete. Black holes are powerful sources of gravitational waves, ripples in space, time that spread outward at the speed of light. When two black holes orbit each other, their immense gravity makes them spiral closer together over time. As they move, they disturb the fabric of space, time sending out waves that stretch and squeeze distances as they pass. When the black holes finally collide and merge, the waves peak in strength, releasing more energy in a few seconds than all the stars in the observable universe emit as light in the same time. These gravitational waves are so strong that they can travel across billions of light years and still be detectable on Earth. The first confirmed detection in 2015 came from two black holes merging about 1.3 billion light years away. Instruments like LIGO in the United States and Virgo in Europe picked up the faint ripples, which changed the lengths of their giant laser arms by less than a fraction of a proton's width. Despite being so small, this signal carried clear information about the size and mass of the merging black holes. Since then, many more events have been recorded, some involving black holes much farther away. Each detection provides new insight into how often black holes form, how they grow, and how they pair up in binary systems. By studying these waves, astronomers can trace the history of black holes across cosmic time. Gravitational waves are different from light because they are not absorbed or scattered by dust and gas. This means they bring us a clean signal of what happened at the source. Even if two black holes merge in complete darkness with no light emitted, the gravitational waves still reach us. This makes them a powerful tool for studying events that would otherwise remain hidden. Future observatories, like the space-based LISA mission, aim to detect waves from even larger black hole mergers, including supermassive ones at the centers of galaxies. These could be detected from billions of light years away, offering a view of the universe's most extreme collisions. Black hole mergers show how space itself can carry messages across unimaginable distances, giving us a way to hear the universe in addition to seeing it. Black holes are some of the most mysterious and powerful objects in the universe, and their influence stretches far beyond what we can see. One of the most fascinating phenomena they create are gravitational waves. These waves are ripples in the fabric of space and time itself, caused by massive events like black hole mergers. When two black holes collide and merge, the immense gravitational forces they generate send waves traveling outward at the speed of light, stretching and compressing space along the way. These gravitational waves are incredibly weak by the time they reach Earth, but they can still be detected, allowing us to observe cosmic events that are otherwise invisible. The breakthrough came in 2015, when the Laser Interferometer Gravitational Wave Observatory, LIGO, detected the first gravitational waves ever observed, resulting from the merger of two black holes. This discovery marked a new era in astronomy, allowing us to study black holes in a completely different way. Before this, Black holes were only detectable through their gravitational effects on nearby objects or by the radiation emitted by the matter falling into them. Gravitational waves, however, offer a direct way to measure the dynamics of these colossal objects, giving us a deeper insight into their properties. The most remarkable aspect of gravitational waves is their ability to travel vast distances. A single wave can come from a black hole merger billions of light years away and still be detectable on Earth. This means that we can observe events from the distant past, such as mergers of ancient black holes, that occurred long before the Earth even existed. As gravitational wave detectors like LIGO and Virgo become more sensitive, scientists expect to detect even more waves from further distances, revealing new cosmic phenomena and providing valuable data on how black holes interact and evolve. Gravitational waves offer a unique window into the universe, one that doesn't rely on light or electromagnetic radiation. Instead, these ripples in space-time allow us to uncover the hidden dynamics of black holes and other extreme events that shape the cosmos. By studying these waves, we're not just observing black holes, we're opening up a whole new way of understanding the universe's most energetic and enigmatic forces. Some scientists think the growth and activity of a galaxy's central black hole can shape the entire galaxy around it. At the core of most large galaxies sits a supermassive black hole, often millions or billions of times the mass of the Sun. When these black holes feed on gas and dust, they can release enormous amounts of energy through their accretion disks and jets. This energy does not stay confined near the black hole. It spreads outward and influences the rest of the galaxy. One way this happens is through heating. As gas falls toward the black hole, it can be blasted outward in powerful winds or jets, moving close to the speed of light. These outflows push against the surrounding gas, heating it and sometimes driving it out of the galaxy entirely. Without cool gas, new stars cannot form as easily. This process, known as feedback, helps explain why some galaxies stop forming stars and become quiet and old. Astronomers have seen evidence of this in galaxies with active galactic nuclei, where the central black hole is consuming large amounts of material. In these galaxies, the energy from the core often outshines all the stars combined, and the jets can stretch thousands of light years into space. These jets disturb the interstellar medium, stirring and heating gas clouds that would otherwise collapse into new stars. At the same time, black hole activity does not always shut star formation down. In some cases, the pressure from outflows may compress nearby clouds, sparking bursts of star formation. This suggests that black holes can both limit and encourage star growth, depending on how the energy interacts with the galaxy's gas. The connection between galaxies and their central black holes is also seen in correlations. For example, the mass of a supermassive black hole is closely linked to the size of the galaxy's bulge, the dense central region of stars. This suggests that galaxies and black holes do not evolve separately, but grow together over cosmic time. By studying these interactions, scientists are learning that black holes are not just passive anchors at the centers of galaxies. They are active engines whose feeding and feedback help shape how galaxies form, evolve, and even die. This makes them key players in the story of the universe's structure and history. Mini black holes, if they exist, would be so small and compact that they could pass through Earth without leaving much trace. Unlike stellar black holes, which form from collapsing stars and have several times the mass of the Sun, mini black holes would be much lighter and far smaller. Some theories suggest they might have formed in the early universe, right after the Big Bang, when matter was packed at extreme densities. These are often called primordial black holes. A mini black hole might have the mass of a mountain compressed into a space smaller than an atom. Because of their tiny size, they would not pull in entire planets or swallow everything around them, as often shown in science fiction. Instead, their gravitational influence would be noticeable only very close to them. If one were to pass through Earth, it would interact with matter along its path, but not enough to cause catastrophic destruction. It would simply continue on its way, almost like a ghostly bullet. The challenge is that detecting such an object would be extremely difficult. Since they are small and emit no light, they cannot be seen with telescopes. They might reveal themselves through gravitational lensing, briefly brightening a distant star as their gravity bends its light, or through gravitational waves if they collided with another compact object. Some scientists have even speculated that high-energy particle collisions, like those in the Large Hadron Collider, could theoretically produce microscopic black holes. If that happened, they would be harmless. According to Hawking's theory, very small black holes evaporate quickly through Hawking radiation, disappearing in tiny bursts of energy before they could interact much with their surroundings. So far, no mini black holes have been observed, but the search continues because their discovery would provide insight into both cosmology and quantum gravity. If primordial mini black holes still exist today, they might even account for some portion of dark matter, the mysterious substance that makes up most of the mass in the universe. For now, they remain a fascinating but unproven possibility. Objects that could drift unnoticed through the cosmos, and even through our planet itself. Black holes have been suggested as possible players in the mystery of dark matter, the invisible substance that makes up about 85% of the universe's mass. Dark matter does not emit or absorb light, yet its gravity shapes galaxies, bends light, and influences the large-scale structure of the cosmos. Since black holes are also dark and massive, some scientists have proposed that they might account for at least part of this hidden matter. One idea is that primordial black holes, formed in the first fractions of a second after the Big Bang, could be widespread across the universe. These would not come from collapsing stars, but from density fluctuations in the early universe. If enough of them survived, they might collectively make up some or all of dark matter. Unlike stellar black holes, which are too rare to explain dark matter, primordial ones could exist in enormous numbers. Astronomers have looked for signs of such black holes using several methods. One approach is gravitational microlensing, where a passing black hole bends and magnifies the light of a background star. Large surveys have searched for these lensing events to estimate how many compact objects exist in galactic halos. So far, results suggest that primordial black holes cannot explain all dark matter, though they might still contribute in certain mass ranges. Gravitational wave detections have also raised interest. Some black hole mergers observed by LIGO and Virgo involve pairs with masses that do not fit neatly into models of stellar collapse. This has led to speculation that at least some of the merging black holes could be primordial and possibly linked to dark matter. Even if black holes do not make up the bulk of dark matter, they may still play a role in understanding it. Their interactions with surrounding gas and stars help reveal the distribution of invisible mass in galaxies. In galaxy clusters, for example, the way black holes shape hot gas may provide indirect clues about how dark matter is arranged. At present, most evidence points to dark matter being made of unknown particles rather than black holes. Still, the possibility remains open that black holes contribute to the puzzle, especially in specific mass ranges that are harder to rule out. If proven, they would connect two of the universe's greatest mysteries: the nature of black holes and the true identity of dark matter. Orbiting close to a black hole would put you in one of the strangest visual environments in the universe. The intense gravity bends light so strongly that it does not travel in straight lines the way it does elsewhere. If you were just outside the event horizon, following a stable orbit, light from all directions could be curved around the black hole and brought into your view. In theory, this would let you see the entire universe in front of you at once. The effect comes from gravitational lensing. Normally, you see objects only where their light travels directly to your eyes. Near a black hole, however, photons from stars behind you can be bent around the black hole's curve and redirected toward you. This would create a warped, layered view of the sky. Objects might appear multiple times, ring, shaped, or stretched into arcs, depending on how their light paths are bent. Simulations show that if you orbited in the so-called photon sphere about 1.5 times the event horizon's radius for a non-spinning black hole, the distortion would be extreme. Light could circle the black hole several times before escaping, so you would see repeated shrunken images of the universe stacked around the black hole's dark silhouette. Stars and galaxies would appear smeared into glowing bands, wrapping the black hole in a strange halo. This view would not be stable for long, since orbits in the photon sphere are unstable. A tiny push would either send you falling inward or fling you outward. But just outside that region, there are stable orbits where the distortions would still be dramatic, though less extreme. From there, you would see the black hole's shadow surrounded by a warped panorama of the cosmos, unlike anything visible elsewhere. The first image of a black hole captured in 2019 gave a glimpse of this effect. The bright ring around the dark core was created by light bent around the event horizon, some of it looping multiple times before escaping. For an observer up close, this bending would dominate the view, making the universe appear to fold in on itself. What you would witness near a black hole is not simply darkness, but a distorted, all-encompassing vision of the cosmos, created by the way gravity reshapes the paths of light. In theory, a highly advanced civilization could use a black hole as a power source, since black holes are among the most efficient engines in the universe. One proposed method is the Penrose process, which takes advantage of a rotating black hole's ergosphere. In this region, space-time itself is dragged along by the black hole's spin. If an object entered the ergosphere and split into two pieces, one could fall into the black hole, while the other escaped with more energy than it had going in. In principle, this extra energy comes from the black hole's rotation. Another method involves accretion disks. As matter spirals into a black hole, friction and gravity heat it to extreme temperatures, releasing enormous amounts of radiation. A civilization capable of capturing this energy could harness far more power than any star produces. Quasars, which are powered by supermassive black holes feeding on gas, shine brighter than entire galaxies, showing just how much energy is available. Hawking radiation offers another possibility. Tiny black holes could emit radiation as they slowly evaporate. If controlled, this steady emission might serve as a compact and powerful energy source. However, producing or capturing small black holes is far beyond current technology, and even containing one would pose unimaginable challenges. Science fiction often explores these ideas, imagining civilizations that build megastructures around black holes to collect their output. A Dyson sphere around a black hole's accretion disk, for instance, would gather not sunlight, but the intense radiation from falling matter. Such concepts remain speculative, but they highlight how black holes could, in principle, provide power on a scale large enough to fuel interstellar civilizations. What makes black holes attractive in theory is their efficiency. While nuclear fusion in stars converts less than 1% of mass into energy, matter falling into a black hole can release up to 40% before crossing the event horizon. For a civilization capable of managing that environment, the payoff would be vast, providing energy far beyond what ordinary stars could supply. Now, far beyond human capability, the idea illustrates how extreme physics might be turned into opportunity, showing black holes not only as destructive objects, but as potential engines for advanced life. Black holes often sound like cosmic monsters, but the reality is less threatening. The closest known black hole to Earth is about 1,600 light-years away, which is safely out of reach. At that distance, its gravity has no effect on our solar system. Even if it were somehow pointed directly toward us, the timescales involved would be immense. Light itself takes 1,600 years to cross that gap, so a black hole would need millions of years to drift anywhere near our neighborhood. Black holes do not roam space hunting for planets to consume. Their gravity works just like any other objects, only stronger when you get very close. If our Sunday were replaced by a black hole of the same mass, Earth would continue orbiting exactly as it does now. We would lose sunlight and heat, but we would not be pulled in or torn apart. This shows that a black hole has no special suction power at long distances. It simply follows the same gravitational rules as stars or planets. Astronomers estimate that millions of stellar black holes may exist in the Milky Way, most of them dormant and invisible. They are scattered widely, so the chance of one coming close enough to Earth to cause problems is vanishingly small. Even when stars end their lives in supernovae and collapse into black holes, these events happen far from our solar system. The radiation from a nearby supernova could be dangerous, but the distances between stars make such risks rare. Scientists continue to monitor the sky for new discoveries, including hidden black holes revealed by their effect on nearby stars or through gravitational lensing. These searches help refine our map of the galaxy and confirm that none of the known black holes pose any danger to Earth. For now, black holes remain fascinating subjects for research and imagination rather than real hazards. They are distant, rare, and quiet compared to the vast scale of space, leaving our solar system undisturbed as they carry out their strange work far away.